Next, I'm Larry Brown's PhD Student Award. It is my very great pleasure to introduce now Yuqi Gu, who was a PhD student of Gongju Zhu in Michigan University, and she's going to talk about identifiability and estimation of structured and hierarchical latent attribute models. You have 45 minutes.
Yeah, thank you for the introduction. So it is my great honor to receive the Lawrence D. Brown PhD Student Award and to speak at the Bernoulli IMS One World Symposium. So I would like to thank the award committee and the organizers for giving me this opportunity. Today, I'm going to talk about identifiability and estimation of structured and hierarchical latent attribute models. This is joint work with my PhD advisor, Gongjun Xu from University of Michigan. First, I want to start with a real-world application to motivate the models. The Trends in Mathematics and Science Study, or short as TIMSS, is an international educational assessment measuring students' achievement in math and science. TIMSS has been held every 4 years since 1995 and covers many countries around the world. Basically, the data we have available from TIMSS include students' correct and wrong answers to a set of test questions. In such settings of modern educational assessment, sometimes researchers are not merely satisfied with using a general score to describe a student's global math ability. Instead, they may want to draw some fine-grained diagnosis of how students perform on the sub-competencies of math. For example, in the TIMSS competence model, researchers have subdivided the math ability into 3 content skills and 3 cognitive skills listed here. And at an even finer scale, they want to understand whether the combination of 1 content skill and 1 cognitive skill is present or absent in each student. That is, whether each student is able to apply with geometry, etc. So now our questions are, how do we uncover students' hidden statuses of either having or lacking the skills based on correct or wrong answers to the test questions? And an even more interesting and more challenging question would be, what are the relations among these 9 latent skills themselves? What are the possible dependency structure there? So based on this goal, it's very natural to consider latent variable modeling. And the latent variable had better to be discrete because scientists' goal there was really to do diagnosis, whether the skills are present or not present. So based on this, in the world of latent variable models, we should actually focus on the bottom right cell using categorical latent variable to model categorical observations. But before doing that, I would like to briefly mention other members in the family. So probably the most familiar one to us should be the factor analysis, using continuous latent variables to model continuous observations. Then, if we believe there are some subpopulations of continuous data, we can move to mixture distribution, such as Gaussian mixture for clustering them. Then if we want to model categorical data, then traditionally in the social sciences, the item response theory models are usually used to understand categorical data using continuous latent scores. Finally, if we move to the world consisting of completely discrete random variables, then a latent class model is a popular approach to model multivariate categorical responses, but using a univariate categorical latent variable. So actually, this is not well suited to our previously defined goal of drawing fine-grained diagnosis of multiple latent skills. Therefore, in this talk, I will focus on a modern generalization of the latent class model. Here, instead of using univariate latent variable, this modern generalization adopts the assumption of multiple latent traits exist to explain the observations. And another key ingredient of this modern generalization is the existence of the structural constraints between the latent attributes and the observed responses. So by this, I mean, not necessarily each observed response, say R1, depends on all the underlying latent attributes. Instead, by some prior knowledge or study design, we can sometimes know that each observation depends only on a subset of the latent attributes, resulting in a sparse dependence graph between the 2 layers. So incorporating these 2 ingredients, the resulting model, we will call it structured latent attribute model. And I like to mention that originally it is psychometricians who designed many models following this general framework, mainly for the purpose of doing cognitive diagnosis. So they are also called cognitive diagnostic model or diagnostic classification model. Yet another name is restricted latent class model, because here we're really building upon a latent class model, but adding this interpretable structural constraints. And as I said earlier, a more interesting question to investigate would be to study the relationship or the dependency structure of the latent attributes themselves. So I will call this a hierarchical latent attribute model. To fix notation, let's first look at the two types of random variables in such latent attribute models. On the observed side, I will use vector R to denote each subject's observed responses to J items, so denoted by vector R with J dimension. And on the latent side, I will use vector alpha to denote the subject's binary states of K latent attributes. So in this talk, both R and alpha are assumed multivariate binary. So keeping this in mind, in the previous example of cognitive diagnosis in education, the goal is to analyze students' abilities in subcompetencies of a subject. Then the observed vector R for each student is his or her correct or wrong answers to the J questions, while the latent profile alpha is his or her profile of mastery or deficiency of the K skills. Here K equals 9 in this particular example. An interesting fact is that in a very different field, epidemiology, researchers actually have been using a similar model to understand disease etiology. And this is shared by Michigan biostats professor. The pneumonia etiology research for child health, or the PERCH study group, they are interested in characterizing the unobserved causes of childhood pneumonia. Then if framed in our terminology, the observed vector R would be each subject's imperfect lab measurements of viruses, etc. While the latent vector alpha would be the presence or absence of pathogens in a subject's lung, which cannot be directly observed. So now I want to introduce the key constraint structure in the latent attribute model through a toy example. So suppose we want to measure two most basic latent skills, doing addition and doing multiplication. And for that purpose, we design 5 test questions. The first question, 1 plus 3, only measures addition. Therefore, it only has one parent attribute in the graph. So here I'm using the word parent attribute in the sense that if there's a directed edge from a latent attribute to an observed item response, then this attribute is said to be a parent of it. Likewise, the 5th item, 5 plus 2 times 3, has both parents, addition and multiplication. Now it's not hard to see that this information of the bipartite directed graph between the latent and observed layer can be summarized as entries in this 5×2 binary matrix, with rows corresponding to these items and columns corresponding to these latent skills. And each row just summarizes the information of what are the parent attributes of each item. For example, the first row is 1, 0, saying that the parent of the first item is just addition. The key statistical property of the family of latent attribute models can be summarized in this key sentence. That is, the distribution of each observed Rj will depend only on its parent attributes in this bipartite graph. To understand this, actually, that is merely saying each student's response to this first item will only depend on whether the student masters addition, but does not depend whether the student masters multiplication. And we should remember that the parent attribute information of each item J is specified by this Q matrix, with entry QJK equal to 1 if attribute K is a parent attribute to item J. This concept of the Q matrix was first proposed by psychometrician Tatsuoka in 1985 and later gained popularity in many modern cognitive diagnostic models. So in this slide, I'm summarizing the model parameters that are used to describe the model. On the latent side, I'm adopting a most unstructured model for the latent profile distribution. So recall that here alpha is a k-dimensional binary pattern. Then I just, for each alpha, give it a proportion parameter p alpha, which represents what proportion of the entire population possess this pattern alpha. Then, given one's latent pattern, it is assumed the responses to the J items are conditionally independent. Therefore, we need some Bernoulli parameters to describe these conditional distributions. And I denoted this by theta J alpha. And it denotes that the conditional probability of providing a positive response to item 1 given your latent pattern being alpha. So note that although I only write one Bernoulli parameter under each item, but in practice, they can take multiple values associated with each item because this value theta can vary as the subscript alpha varies. There are indeed many models following this general framework. Then they model the theta parameters differently, but they share the key commonality summarized in this colored box. And this actually exactly corresponds to the previous key sentence in my last slide. In my last slide, I said that the distribution of each Rj depends only on the parent attributes. Now that the distribution of R is characterized by theta, so probabilistically, the constraint on the parameters is that each theta j alpha is not freely varying in 0 and 1. Instead, they depend on the parent attributes specified in Q. So now I'll give a concrete example. The most popular and basic model in the family probably is the DINA model, short for deterministic input, noisy output, and gate model. It assumes that basically each item categorizes all the latent patterns into two categories, the capable category and incapable one. Then if a latent pattern alpha possesses all the parent attributes of the item J, meaning that this latent profile has all the required skills of some question J, mathematically in this form, then this pattern will be considered capable of the item, but still can have a slip probability Sj to make a careless mistake. On the other hand, if the pattern alpha lacks some parent attribute of item J, then the pattern will be considered incapable of this item, but still can have a guess probability Gj to make a lucky guess. DINA is a very popular and basic model for modeling education data, and it actually can serve as submodel for some more general members in the family. For example, the main effect model, all effect model, as I said, they can take different forms in modeling theta, but they share the commonality that theta only depend on parent attributes through these QJK entries in the formulation. So these models in this slide will be called a multi-parameter model, because instead of using only two parameters in the DINA case, the sleeping and guessing probabilities, here for each item, there can be multiple values of parameters. Interestingly, the deep Boltzmann machine proposed in the deep learning literature can be viewed as a main effect latent attribute model with a sigmoid link function. This is because both our latent attribute model and the DBM assume that the latent variables and observed variables can be represented as multivariate binary, and there are links between the layers, but not within each layer. So as said earlier, a focus of this talk would be the hierarchy among the latent attributes themselves. And here is a toy example of how this can be possible. So remember that there are 3 cognitive skills related to 4th graders math in the teens model. There are know, apply, and reason. So since everything is binary, the 3 skills will result in 8 skill profiles listed here. 1 row for profile. For example, the first row just represents a skill profile not possessing any skills and defines a student subpopulation, which has proportion T000 in the population. And there are 8 such subpopulations. The proportion parameters are non-negative and they sum to 1. Now, what if I tell you, I believe a student must first know before she can possibly apply, before she can possibly reason? This type of belief on the hierarchical structure of the skills actually rules out certain skill profiles from existing in the population. For example, a student on the 3rd row who only knows, who only applies but does not know, cannot exist in the population under this hierarchy. Therefore, the P010 should be constrained to 0. In fact, under this particular hierarchy, only the 4 latent profiles on the right panel can exist with non-zero proportions, and the summation of this still gives 1. So from this toy example, we can see that actually an attribute hierarchy would lead to degenerate parameter space for the proportion parameters, or equivalently, it will actually define what are the permissible latent patterns with positive proportions and what are the forbidden latent patterns that should be having a zero proportion. This attribute hierarchy model or method was first proposed by Latent et al. 2004 for doing educational assessment. And in that paper, they actually considered the following so-called hierarchies: the linear hierarchy, convergent, divergent, and unstructured. And since then, this hierarchy method actually has attracted much attention, not only in the educational and psychological field, but also in computer science, so in the educational data mining and machine learning. But the key theoretical property as to in what cases are these latent hierarchies learnable is unclear in literature. So as a glance at the challenges, recall that I use capital K to denote the number of binary latent attributes. Then as the capital K increases, the number of latent patterns, the entire, the number of all the possible latent patterns may increase exponentially with K. And the interdependency, for example, the attribute hierarchy graph among the K attributes can become more structured. Also, the Q matrix, which summarizes the study design information, can become increasingly complex as well. So on this slide, I'm summarizing my views of the advantages and the challenges brought by this latent attribute modeling. So the advantages include that because we have the multiple fine-grained attributes, so they can carry interpretable substantive meanings. And also the Q matrix summarizes the study design information or encode the scientific prior knowledge. So also is very useful in modeling. In addition, the attribute hierarchy graph can encode the sequential acquisition of some latent traits. And by having an understanding of this attribute hierarchy, we can actually inform future educational intervention, for example. But together with these gains brought by this type of models, we also have the challenges. For example, the many discrete unobserved attributes themselves can bring challenge in estimation and theory. Also, the complicated constraint structure imposed by the Q matrix and the degenerate parameter space caused by the attribute hierarchy graph also pose challenges. So the research questions I want to investigate include the theoretical identifiability issue. That is, when are the latent structure and model parameters uniquely recoverable, under hierarchy or without hierarchy? And the methodology question is, how should we seek the meaningful solutions of attribute hierarchy in a potentially large latent pattern space? The focus of the talk will mainly be about the theoretical identifiability issue. So identifiability in layman language basically means, based on the observed data, the model parameters of interest can be uniquely recovered. And this is usually a problem to watch out for latent variable models. And for this complicated family of latent attribute models or diagnostic models, I want to briefly present what empirical researchers view this problem. So we can see that in the past 2 decades, empirical researchers working on psychological and educational measurement have noted the difficulty and the importance of finding out the identifiability. And also noted that identifiability seems to be increasingly difficult with increasing number of skills in the model and is much harder than some other models. So now I want to formally introduce the definition of identification. Under the previously introduced model setup, the distribution of our observed vector R can be written in this form. So it is actually a mixture model, and it is a mixture of product Bernoulli distributions under our previous assumption. And using this graph, I'm reminding you the model parameters of interest. They are shaded in pink. On the latent side, we have the proportion parameters P alpha. And remember that if there is any attribute hierarchy, then certain P alphas will be constrained to be 0. And on the observed side, we have the Bernoulli parameter theta describing the qualities and characteristics of the observed items. And the Q matrix implicitly plays a role in constraining these data parameters, although I didn't write Q matrix in this definition. So equivalently, this distribution of R can also be written as a J's order tensor, with this notation corresponding to a tensor order product. And recovering parameters from the observations R is actually a problem of constrained tensor decomposition. Constraint because we have the Q matrix constraining the model parameters. So here come the several definitions of identifiability. First, traditionally, people have asked the question that if we know a Q matrix, when are model parameters theta and p identifiable from data? So this type of result can be important for confirmatory analysis. But a more challenging question would be, what if we do not know Q? And in an entirely exploratory analysis, we want to estimate both the Q matrix and the model parameters. Then even a more challenging question is to ask, what if we do not know Q, and what if there is some unknown attribute hierarchy constraining the parameters? Then the question is, based on the observations alone, how can we determine from data the Q matrix, the hierarchy, and all the related model parameters? So my talk will focus on the second definition and the third definition here. Now I want to briefly talk about what are statisticians' progress on identifiability in discrete latent variable models. Indeed, since the latent class model was first proposed in Lathersfield 1950, it was not until 1994 that Gillenberg et al. Brought some not so good news, saying that unrestricted LCM is not identifiable. But fortunately, in 2009, Allman et al. In a seminal paper established a slightly weaker notion, the generic identifiability of unrestricted LCM. Note that these don't deal with the constraint structure, for example, our Q matrix structure, so they are not applicable to latent attribute models. But very recently, in the literature, there are some works that consider the estimation and identification of latent attribute models. Then what are lacking in the literature and what motivates the current study? I'd like to investigate the three sub-questions here. The first sub-question is regarding the necessity of the sufficient identifiability conditions. Because most studies existing in the literature, they consider what are sufficient for identification. But in my study, I want to ask, where is the theoretical boundary between the necessary and sufficient conditions? And this can provide the sharp answer to identification criteria. And the sub-question number 2 is, can the strict identifiability notion be relaxed reasonably to allow for broader applicability? And the third sub-question is a focus. It is regarding identifiability in the existence of the attribute hierarchy, because to our knowledge, none of the works in the literature have considered identification in the existence of the attribute hierarchy graph. And this is indeed a much more challenging problem. So I will just briefly talk about the first two and focus on the third one. So for the first question, one of our main results is as follows. We established the necessary and sufficient conditions for identifying the entire latent structure, including the Q matrix under the popular DINA model. It is very interesting and somewhat surprising to find out that the necessary and sufficient conditions can be succinctly written as 3 algebraic properties of this Q matrix. The first condition is Q contains an identity submatrix, IK. The second is each column should contain at least 3 entries of 1s. And the third condition is, other than this identity submatrix, the remaining submatrix of Q should have K distinct column vectors. So this can be intuitively understood as, other than those pure items that only measure some single scales, the remaining items in the test should have enough variability to tell the K scales apart in these K distinct columns. So I will also call the condition A0 as a completeness condition, because it shows that the test needs to be complete in that it should require all the scales solely by some item. And the condition B0, I will call it repeated measurement condition, because it requires each scale to be measured at least 3 times throughout the exam. And condition C0, I will call it distinct column condition. I will revisit this concept later. The implications of this theorem includes that It fully solves the identifiability problem under the popular and basic model. And it characterizes the minimal requirement for designing valid diagnostic tests under DINA for practitioners. So if the practitioner wants to design future tests to measure students' abilities, then these are the minimal constraints they need to follow. As I promised in the second part, second sub-question for identifiability is a more relaxed notion of identifiability. And this is motivated by considering that the strict identifiability condition that Q contains an identity sometimes is hard to satisfy in practice. For example, here is part of the Q matrix corresponding to a real data set, TIMSS 2003 8th grade data. And among the many row vectors I'm presenting here, only the first latent attribute gets solely measured by some questions. And all the remaining latent attributes are always simultaneously measured with some additional attributes. This is quite common, and it is desirable to investigate what conditions can lead to some identifiability guarantee here. So this motivates us to consider the generic identifiability for the latent attribute model family. The strict identifiability result that I presented earlier basically means parameters should be identifiable everywhere in the parameter space. But generic identifiability makes a little bit compromised, only requiring parameters are identifiable almost everywhere, in the sense that it can accept a Lebesgue measure zero set from the parameter space. So here is just a graph illustration of this concept. Suppose our parameter space is a 3D object, a 3D tetrahedron. Then if all the non-identifiable parameters live in this settled surface within this tetrahedron, then the model can be considered generically identifiable. And from this example, we can also see that although it is a slightly weaker notion, but it can suffice for real data analysis purpose. Because as the true parameters vary almost everywhere in the tetrahedron, it will not likely to touch upon this surface, and we're good. Identifiability can be ensured. So regarding this notion, we established the following conditions are sufficient for generic identifiability for multi-parameter latent attribute models. The first condition says that the Q needs to contain two K by K submatrices, Q1 and Q2, such that each of it has all the diagonal entries equal to 1, but any of the non-diagonal entries are free to be either 1 or 0. The second condition says that in the remaining Q star submatrix part, each column needs to have at least one entry of 1. So from these two conditions, we can see that we no longer require the Q to contain any identity submatrix, which is a huge relaxation of existing conditions and can be more applicable in practical scenarios to guarantee identifiability. More results can be found in our paper. Now let's move on to the third sub-question, that is, can we obtain identifiability in the existence of a non-empty attribute hierarchy graph? So I will introduce some basic setup here. In our previous results, we made the key assumption that P alpha is greater than 0 for all the possible latent pattern configurations. And this actually rules out attribute hierarchy. And next, let's consider that P is actually 0 for some latent profiles. So here I will use the big epsilon to denote an attribute hierarchy. And it is indeed a set of prerequisite relations among the latent attributes. Here, K to L would denote attribute K is a prerequisite for attribute L. And probabilistically, it puts a constraint that any attribute pattern that does not possess the basic attribute K, but possess the more advanced attribute L is forbidden and should have proportion 0 in the population. And naturally, the attribute hierarchy graph will lead to a concept of the reachability matrix among the attributes. So the reachability matrix is a K by K binary matrix. And it is actually a concept related to the graph theory. It has all the diagonal entries equal to 1. And for the non-diagonal entries, the EKL would equal to 1 if L is a prerequisite for attribute K. We can see this from this toy example that suppose we have a hierarchy where alpha 1 is the most basic attribute, and it serves as prerequisite for the remaining 2 attributes. Then we would have the 2-1 position and 3-1 position of the reachability matrix equal to 1. So the reachability matrix actually will induce equivalence relation of all the design matrices Q. And this can also be easily seen from this toy example. So in this toy example, we have that attribute 1 serving as prerequisite for the additional attributes 2 and 3. Then we can see that actually the identity matrix I3 will be equivalent to the reachability matrix. To understand this, let's focus on the second row. The second row vector is actually can represent an item, a question that only measures the second skill. But because the second skill requires the first skill as prerequisite, therefore, this type of question in the test actually is equivalent to a question that measures both skills, 1 and 2. Therefore, we have this epsilon equivalence relation. Then based on this relation, we introduce the following 2 useful operations on Q matrix that will be useful in our identifiability theory. So the first operation is a densifying operation. It says that for any QJH equal to 1 and K is a prerequisite for H, we will set the QJK also to 1. So by this operation, apparently the resulting Q matrix will be denser, and we will call it a densified Q matrix. On the other hand, for QJH equal to 1 and attribute K prerequisite for attribute H, we will set QJK to 0, and this more sparser Q matrix will be called a sparsified version of the Q. There are always the following relationships. The identity matrix through the densifying operation will become the reachability matrix, and the reachability matrix through the sparsifying operation will become the identity. So from this, we can also see that either the densifying operation or the sparsifying operation only modifies a Q matrix within the same equivalence class, because IK is always equivalent to E. Now we're ready to state one of our main results in the identification of hierarchical latent attribute model. The following 3 conditions are sufficient. First is the sparsified Q matrix should contain an identity matrix. And the second condition is the sparsified Q should have at least 3 entries of 1 in each column. And condition C is the densified Q contains a reachability matrix, and the remaining submatrix should have K distinct column vectors. So from the statement of the theorem, we can see that it is related to our previous result about the necessary and sufficient condition for DINA, but we have this sparsifying and densifying operations coming to play. And indeed, these conditions A, B, C, I will call it epsilon completeness, epsilon repeated measurement, and epsilon distinct column condition. And actually, when this attribute hierarchy graph epsilon is an empty graph, meaning that there's no prerequisite relationships among skills, then in this case, the current conditions A, B, C will reduce back to the previous conditions A0, B0, and C0. So based on these relationships of the 2 sets of conditions, it's not hard to see that actually when the attribute hierarchy graph, in the special case, when epsilon is empty, then these conditions reduce back to be necessary and sufficient. But actually the necessity of these conditions are more subtle than this statement. So let's look at them in more detail. So first about the condition A. The condition A actually is still necessary for identification, which is stated in this proposition. Recall that in our previous result, we also have that when there's no attribute hierarchy, the previous condition A0, that Q contains an identity, is also necessary. So from this current position, it seems that the attribute hierarchy graph does not seem to play a big role on changing the necessity of the epsilon completeness condition. However, does this also apply to conditions B and C? Originally, I thought this was the case and tried to prove it. But later, through careful derivation, I found it is not the case, and it's very interesting. So here's a counterexample. So recall that Latent et al. 2004 specified that this is called a divergent attribute hierarchy among the 6 attributes. And I found out that actually a Q matrix that contains 2 copies of the reachability matrix can suffice for identifiability. But in this case, actually, the attribute k equal to 6 violates the repeated measurement condition, because if the Q matrix contains 2 copies of E, then we can see that the 6th attribute is only required by 2 items. So it is not required by at least 3 items as stated in condition B, and condition B is violated here. So more generally, we actually have a proposition that for any common ancestor type of attribute hierarchy, a Q matrix containing 2 copies of reachability matrices would suffice for identifiability. And a common ancestor hierarchy just means that there exists some attribute that serves as a prerequisite for all the remaining attributes. Indeed, the previous 4 types of attribute hierarchies in Latent et al. All belong to the common ancestor attribute family, hierarchy family. So this motivates us to look more closely at the different roles played by different attributes in the graph. And here are the 4 categories of attributes that we introduce. For example, if an attribute is not connected to any other attribute, then we will call it a singleton. Then if an attribute has some prerequisite, but does not serve as a prerequisite, it will be called a leaf attribute. And similarly, we can define ancestor and intermediate. So if there is no attribute hierarchy and epsilon equals the entity graph, then all the attributes are actually singletons under our definition. Indeed, under the linear hierarchy, we found out that the necessary and sufficient identifiability condition can be written as condition A and the following condition D here. So condition D says that the ancestor and the leaf attribute should be measured by at least 2 items, but any intermediate attribute only need to be required by at least 1 item throughout all the items. So the D condition is actually in replacement of the previous repeated measurement condition B. And interestingly, this phenomenon about attribute types holds more generally. Here we have 3 results characterizing the requirements for different types of attributes in the graph. So for singleton attributes, we need these attributes to be required by at least 3 items throughout the test. And this is necessary for identifiability, and also there exist identifiable cases where this equality in A is actually achieved. And similarly for ancestor and leaf attribute, this requirement is reduced to 2, and for intermediate attribute, this requirement is actually reduced to 1. And also we consider the necessity of the epsilon distinct columness condition. And also it turns out that this condition is not overall necessary. Instead, its necessity will depend on the relationships among the attributes. And I will not go to the details here. But we also have graphical illustrations, and you can simply follow the conditions to check whether these 2 attributes, they have distinct columns and whether the model is identifiable based on the theory. So as a short answer to the sub-question 3, can one obtain identifiability in the existence of a non-empty hierarchy graph? The answer is yes. And the identifiability conditions are actually related to the case when the hierarchy graph is empty. But the conditions here are more subtle and more technically involved, especially regarding their necessity. And these conditions also reveal the trade-off between the hierarchy graph epsilon and the design matrix Q. Generally, it can be summarized as the more information an attribute K has available from epsilon, the less requirement on the design matrix is needed for this attribute to establish the identification. And this is a graph summary of the condition B. So in condition B, we established that for a singleton attribute, we need it to be measured by at least 3 times. But for ancestor and leaf, which has some one-sided information in the hierarchy graph, we can relax this requirement to 2. While for intermediate, we can further relax the requirement to 1. So our conditions characterize the fine boundary between the necessary and sufficient conditions. So a short summary to the identifiability issue for latent attribute models is that we have some conditions that are transparent because they only depend on Q or the attribute hierarchy graph, but does not depend on the values of those model parameters such as theta or P. Therefore, our conditions are easily trackable, and they sharply characterize the roles played by different types of attributes. And they can serve as useful guidelines for practitioners to design their test under a potentially complex hierarchy. Then about the methodological estimation problem. That is, how do we estimate the attribute hierarchy and seek meaningful solutions from a potentially large latent pattern space? So here is a motivating example. Still for the team's 2008 8th grade data, researchers interested in 13 skills, but available sample size is 757, which is much smaller than the possible number of configurations of skills. So what latent skill patterns exist? Now I will introduce a notation, which is the set of truly existing latent patterns. It is also related to our attribute hierarchy graph. So recall this vector P is the population proportion vector for the latent attribute profiles, and it lives in the simplex. So I will collect all the truly existing patterns in the set script A0 to be those patterns which have positive proportions. Then if this vector P is dense, then A0 just equals to the entire set of possible configurations. While if this P is sparse, then A0 just collects those allowable attribute patterns or the support set of vector P. So in the real world scenario, when K is large and sample size is limited, we have 2 reasons to believe that script A0, the set might just be a small set of the entire set of configurations. The limited sample size reason and also the attribute hierarchy reason. So how to find that out? Our answer is we should seek the sparsity structure of this high dimensional vector P, which lives in a simplex. And here is our proposal. To encourage sparsity of this vector P, we propose a regularized likelihood approach. Here, the L theta P denotes the log likelihood under the model setup. Note that Q matrix implicitly plays a role here. And the blue part corresponds to the regularization. And lambda is a negative tuning parameter. It is a log summation of log type penalty of the proportion parameters. And the larger value lambda takes, the larger magnitude lambda takes, the more shrinkage we're adding, and the sparser the resulting solution of P would be. In practice, we will seek the maximizer and do the latent pattern selection by thresholding the estimated proportion parameters. And an important motivation for adopting such a log type penalty instead of other more popular methods for sparsity producing penalties is because this can actually allow for an easily modified EM algorithm to solve the problem very easily. And also another motivation is that this penalty actually also has an alternative Bayesian understanding. So recall we have a lambda times sum of log terms. And by taking the exponential function, it will actually become this form. And it is proportional to a Dirichlet density. And the Dirichlet density has a property that if this lambda is negative, then the Dirichlet density surface just puts more concentration towards the corner of the simplex. Here, it is a Bayesian understanding because we view this P not as parameters, but as random variables distributed in the simplex. Then, when lambda is negative, our penalty actually corresponds to a prior belief that these P's are actually sparse in the simplex, and it corresponds to our sparsity pursuing goal. But an important difference between our proposal and this classical understanding is that a proper Dirichlet prior distribution should have this lambda greater than -1, so that beta is positive and it is well defined. But in our approach, we allow arbitrary magnitude of this lambda, and we establish latent pattern selection consistency. In that when sample size goes large, our probability of exactly finding out the truly existing latent patterns goes to 1. And allowing lambda to have arbitrary magnitude is important here. And I will briefly present a numerical example illustrating the approach. So here I'm generating data using 10 latent attributes. And out of the 1,024 possible latent patterns, I'm randomly selecting 10 of them as truly existing patterns, plotted as each row on the left panel. And each pattern has population proportion 0.1. And I use a Q matrix with 30 rows or 30 items for generating the data. And here is a numerical result. This is a truly high dimensional scenario because the possible number of latent patterns, 1,024, far exceeds the sample size 150. And I'm plotting the solution paths of the estimated proportion parameters P versus the tuning parameter lambda. And out of for all the 10 true latent patterns that I use to generate the data, they are plotted in 10 different colors, while for all the 1,014 remaining patterns that not exist in the population, I plotted in black. And we can see from this solution path that selection is successful when the tuning parameter is between -4 and -1.4. In that all the colorful true patterns get selected with positive P, while all those non-existing patterns just vanish and don't get selected. So note that here lambda is less than -1. So my answer to the second part is that we have a regularized likelihood method with a penalty on the mixture proportion parameters of the high dimensional latent classes. And through this, we can select what are significant patterns in the population. And further, we can go back to recover what are the hierarchical structure among attributes. So this is still a toy example to illustrate this idea. Suppose our estimation approach output these 4 latent patterns as a significant pattern. Then this is indeed a binary matrix, and we can examine the partial order between the columns of this matrix. For example, here the column corresponding to knowing is element-wisely greater than or equal to the column corresponding to applying, which implies that knowing is actually a more basic skill, and there is a prerequisite relation from knowing to applying. Based on this rationale, these 4 patterns would indicate the linear hierarchy among the skills. Combining this rationale and our estimation methodology, we analyzed the data set I mentioned in the very first in this talk, which is the TIMSS 2011 Austrian data, measuring 9 skills. And we discovered this hierarchy. There's something intuitive here. So among the 3 content abilities, geometry, number, and data, it seems that geometry is more advanced. Among the 3 cognitive abilities, reasoning, knowing, and applying, it seems that reasoning is more advanced. And this is estimated through a latent pattern selection approach, while most existing studies either assume all the 2 to the power of k combinations of latent patterns exist, or pre-specify some certain hierarchy based on consulting on the domain expert's belief. But our approach can provide exploratory analysis of the hierarchical structure. As a conclusion of my talk, in a large complex latent world, we have addressed the identifiability issue by proposing some transparent conditions. And these conditions can guide future designs of cognitive diagnosis tests or other diagnostic tests under the attribute hierarchy. And the theoretical results are actually corroborated with numerical studies to validate. And methodologically, we propose a regularized likelihood method to consistently and efficiently select what latent patterns are significant. And based on this significant latent patterns, we can further examine what are the attribute hierarchy graphs. And we also have numerical results to validate that this approach is effective in recovering different types of hierarchy graphs. These are more references, and thank you very much for your attention. I'm happy to take questions.
Thank you very much for this fascinating talk. Are there any questions from the audience? I have a few myself, but I want to wait until there are more. Okay, so I'm going to start the story. So I have a question regarding your identifiability issues. Can you identify as well K?
Oh, yeah, that's a very good question. So in this talk, I focus on the case where K is assumed known. And in practice, when K is overfitted, for example, the true K that generates the data is 5, but we assume that an arbitrary number K is possible to generate the data, then actually the problem cannot be strictly identifiable, because those additional attributes, we can just specify the columns in the Q matrix to be all 0, or just merging some attribute profiles such that they can still, with attribute number equal to 10, they can still provide the same distribution of the responses. So a short answer is that theoretically, we need to know the number K, but in practice, through some other regularized estimation approach, I think K is also estimable, can also be estimable from data.
Yeah, so that, yeah, my question was about the estimation possibility. It's a bit like mixtures when you don't know the number of components, because this is very similar to what you're looking at. Of course, if you have overspecified K, so if K is too large, then you're not identifiable, but you can still estimate the true number of classes by considering the minimal possible number of classes. So that's what you're thinking about?
Yeah, and actually that is also related to our current estimation, regularized estimation method I described here, because indeed this is actually estimation from an overfitted mixture model, because here, although I assume I know K, but as I said, when K is large, the number of possible configurations of mixture components is 2 to the power of K, but the significant ones or the ones that generate the data might be a small number. For example, only 10 out of 1024. So actually the likelihood part is an overfitted mixture model. And in order to estimate what are the significant mixture components, we're actually imposing the regularization in order to estimate, to empty out those redundant components. And these are characterized by the sparsity structure of this vector P. So yes, it's very related to what you were talking about.
So in your penalized likelihood approach, you do not try to constrain your structure to be like a DAG or something for the hierarchy. You're not trying to learn the structure. You're only trying to learn the zeros and non-zeros of P alpha, essentially.
Yes, yeah. Yeah, so in this approach, actually, we are not directly modeling the edges. I mean, in this estimation approach, we did not directly modeling the edges of the graph, but instead, we aim at estimate what are the significant patterns, and then go back to examine the edges among the attributes. So yeah, we did not directly focus on these edges, but I think it would be an interesting future direction to consider that if we can directly estimate the hierarchy graph without imposing that all the 2 to the power of K combinations are possible to exist.
Thank you. Are there any other questions? I have a last one. I haven't seen anything related to label switching in your problem. Is there absent in your model a label switching issue that you encounter in mixture?
Yeah, you mean is label switching an issue here in estimation? or in identifiability?
Yeah.
Oh, yeah, that is a very good point. I didn't mention it, but first comment is that actually I introduced 3 types of identifiability definitions. The first is if a Q matrix is known, and we study when the parameters can be identifiable. So in this case, we don't have a label switching because Q matrix is like an analog of factor loading structure. So in this case, it is not an issue. But indeed, for the cases when we have entirely exploratory analysis and the Q matrix is unknown, then this identifiability are actually in the sense of up to label switching, which means that it is not very rigorous to write this equality, but this equality is in the sense that only up to inevitable label switching of the columns of the Q matrix, because the columns of the Q matrix correspond to different latent attributes. And the best we can do if we do not have the Q matrix itself as known, the best one can do is to identify the Q matrix structure up to the label switching of these latent attributes. Yeah, but still, this is a meaningful identification result because we can always rearrange the columns of the Q because the columns are distinct if the identifiability is satisfied. So we can always reorder the columns. So this issue can be resolved.
Yeah, thank you very much. And I have just like a short question before we sort of have to close the discussion, but you use the EM algorithm in your approach. Have you encountered some kind of local mode problems or in practice, or not so much?
So yeah, in theory, the local mode issue is a huge problem for EM algorithm. But in my experience, actually, the EM type algorithms work fine here. In producing the simulation results, we need to randomly choose the starting points, but just a few different starting points can lead to good estimation accuracy of the latent pattern selection results. Yeah, in my experience, in this case, EM algorithm works reasonably well.
Thank you very much. Well, I think we have to close the discussion. Thank you very much for the fascinating talk that you gave. It's very, very interesting. And bye.